So today we start one more lecture. It's the 8th lecture of our course. So we are getting to a half of the course. And today's lecture is about statistics. So you may be wondering, why am I making a lecture on statistics in this course? There are basically few reasons. The first and the foremost reason I want to remind you something about statistics is the fact that machine learning and data science can be treated in some sense as a statistics on steroids. So you are like making the same plain good, old good statistics, but the statistic that you make is equipped with some modern methods. So you are using like some modern libraries, you're using Python, you're using some different complicated methods. But at the end of the day, you get some sort of statistical information that can be further processed or used to make some decisions. And of course, everything we have in statistics will influence somehow what we do in our machine learning and how we understand. The second reason is the fact that you will be probably using even some things from, let's call it some old statistics, when you are doing machine learning. So for example, if you have a few models and you are performing so-called A/B testing, so you want to know which model is better. And you have to plan your experiments, collect some data, and make decision which model is better, so model A or model B, based on that data you have collected. And of course, all the information processing and gathering that information you will be doing in a realm of statistics. So you should be able to process that information correctly and correctly get all the data, well, make some correct decisions based on the data that you collect. So that's the second reason. Okay, so let's get quickly through that. So what is statistics? So statistics does basically what? Collection, organization, displaying, analysis, interpretation, and presentation of data. So that's some sort of very broad discipline. What I want to start from, so there are, let's say, two main statistical methods that are used in data analysis. So that's descriptive statistics. So it's some sort of collection of methods that summarize data from a sample using different indices like mean, standard deviation, so on and so forth. So you are having a bunch of data and you want to create some sort of description of that data. That's pretty obvious reason in the sense that if you are collecting data and you have 1 million of data points and you want to know something about all the data points, of course, you won't be looking at all that data points at once. You just cannot process so much information. But if you are calculating some sort of numbers that describe all that million of data points like mean value, standard deviation, so on and so forth, you are getting some insights into that data with a reasonable amount of numbers that a human can process. So it's all about interaction with humans and machinery. So machine can process 1 million data points. That's okay. You cannot. So you have to retrieve some manageable amount of numbers that you can process to have some understanding of that data. And the second branch is so-called inferential statistics, which helps us to draw conclusions from data that are subject to random variation. So we always have some observational errors, some sampling variations, so on and so forth. And we need to be able to draw some conclusions, taking all that randomness into account. So what I start with is two terms like population and sample. What is it all about? So first of all, you can ask a question: can I collect all possible data? Answer can be yes, that you can gather all that data and you will call that a population. Or the answer is no, you can gather only some of the data and you will call that a sample. In the real world, of course, we expect that we never can collect all the data because most of the practical problems, they are you just cannot. So for example, if you are, I don't know, recognizing some cats, you cannot make a photo of each cat in the world from each possible point of view. So that's impossible. So of course, whatever data you get, in most cases, that will be just some sort of sample. So you cannot get all data in the world. Here is some sort of example, like population versus samples. So the population contains all possible information. In some cases, it's some sort of exists. In some cases, it's some unmanageably great set that you just cannot ever have. And what we have in the real world is some sort of samples. And our samples, they can be, let's call it representable or unrepresentable. And that means that either their properties more or less coincide with the properties of the whole population. So in this case, they are representative, or they do not coincide and they are unrepresentative. Probably you have heard something like that when you, I don't know, when listening some news about exit polls, and they say that, well, we have some sort of, I don't know, presidential elections. We are running that elections, and we have two candidates, and we have collected a sample of people. We asked them, who will you vote for? And we have a representable sample that tells us that this one will win or that one will win, and so on. And that representable sample, with that representable sample, they mean that they try to collect data in a way that small sample that they have, because they cannot ask everyone in the country who will he vote for, and so on. So it's just a small sample, I don't know, a few, maybe thousands of people, but they are trying to make that sample representable and to have all the properties that the general population has. In most cases, we will want that. And if you are collecting some data, you will probably need to think that may be the case that you want your sample to be representable, and which properties are you measuring, which properties are influencing the result that you have, and and what you should do to make your sample representable. Okay, this part we will a bit talking about in the previous lecture, so I'm not getting very deep into that. I'm just reminding you that there is a really nice model like sack with some sort of balls, and we are growing that balls, let's say blue and red balls. And we may get different distributions that we further use basing on the model, basing on this model, let's say. So you can either grow just once a ball, or you can grow multiple times, and you can grow, I don't know, some fixed number of times. Let's say make n trials, or you can try until some number of failures. So let's say you are growing balls up to the point when you get 10 red balls, and so on and so forth. And depending on that, you have different distributions like Bernoulli, binomial, hypergeometric. And of course, you have one more thing to tune. When you are getting a ball from the sack, you can either just skip it, or you can return it to the sack. The more easier case to analyze it's when you're returning that into the stack, just because in this case you are not disturbing the probabilities of getting different balls from there. But if you are not, you once again you can have some sort of distributions. In this case, they are called negative binomial or negative hypergeometric. So I'm just reminding you that, nothing more. Types of data. What I want to tell you about the data, well, when we are collecting some data, we are just, let's say, creating some sort of data points from features. But when we are creating our data points from our features, we should remember that these features, what are they? Some sort of measurable characteristics of the object under consideration. They may have a different nature. And depending on that nature, you may or you may not perform some operations on that features. Of course, you have already, I don't know, some sort of guess that some features that you might have, they are sort of discrete. So you can't have some, I don't know, number of chairs like 4.5. You may have only some integer number of chairs, while some other features like, I don't know, temperature, they are real valued, and you have some real value like 45.7 degrees of Celsius and so on and so forth. But there are some more subtle things to that, and now I want to show you like types of data that we have and what can we do with that data. So when you are performing some sort of data processing, then you can split your features into categories and think that with these features I can perform like these manipulations, and with that features I cannot perform. So the first and the foremost split of data types, it's like we are creating two branches, a branch of categorical features or categorical data, and numerical features or let's say numerical data. So the first one represents some sort of characteristics, while the other one represents quantity features. So there are some characteristics of objects that you cannot like express with numbers, or you can do that, but these numbers won't have any let's say meaning. So for example, you are studying, I don't know, some group of people, and you have a characteristic whether some human is a student or his or she is not. And of course, in some sense, you can represent this feature as, let's say, 0 or 1. So is student, is not a student. But maybe you are guessing at this point that it's not like true number. So you can just add that zeros and ones and get some sort of meaningful results, or take some mean value and so on and so forth. So that will be a bit strange. So you can't have, I don't know, 1/2 of a student or something like that. Or someone cannot be a half student. So either he or she is student or not. And further division that we get to, we are dividing categorical features into nominal features. These are discrete units or labels that characterize your object. So for example, it can be some name. So if you are, once again, you are studying people, you have some sort of table with that people, and you are doing some analysis, maybe you will have a column name, and name is a sort of nominal feature. Or it can be gender or a language that one uses. So these all are nominal features. The other type are ordinal features. These are, once again, categorical features. So even if you are presenting this data in your table with some sort of numbers, it's not like numbers that we all are used to. So you can do certain operations on them. But this data is naturally ordered. So for example, I can describe people like tall or I don't know, medium, small, and so on. And I can order them according to this description. Now let's get to numerical data. So numerical data represents some quantitative features, and these data can be, for example, interval data. That numbers from the scale with order and exact difference between values. So this means that difference between values means something. I will show you an example of that. So for example, that can be degrees of Celsius or Fahrenheit. Or the last type of data is ratio. That's numbers from the scale with order, difference, and absolute zero. So for example, Celsius and Fahrenheit, they don't have like absolute zero. But Kelvins, for example, or when you are measuring a mass, they do have. So here are some more examples of like nominal data, like blood type, so on and so forth. But what I want you to show is this table. This table shows you which types of operations you can perform on your data and what can you extract from there. So for example, nominal data, you can calculate some sort of counts. So if you are, I don't know, creating a table and you have a column like language that one uses, you can calculate number of users, let's say of English or German or French and so on and so forth. So you can find counts. You can find so-called mode. This is the value that you see most often in that column. For example, you can find out that, I don't know, the majority of people uses, for example, English. And that's okay. But you don't have any order. You can say that English is bigger than German and so on and so forth. You can't find any median. You can do that just because you don't have any order. Differences have no meaning for these data. You cannot calculate English minus German. Even if you are representing languages in some sort of numeric way, so you have prescribed some numbers to them and you are collecting numbers into that column, you still cannot calculate the differences because you cannot give them any meaningful interpretation. And of course, you don't have any mean values, so on and so forth. On the other hand, ordinal data. It can be something that you describe with the words like large, small, so on and so forth. So this is some sort of data that you are like describing, but you have some internal order to that data. So this data can be ordered. It looks like a small change because you had nominal data, you were describing something with words, and once again you're doing the same thing, and what of that you have some order. But having that order makes possible to have median for that data. So you have some new abilities to process that data. You can calculate median and you can do something with that median, despite the fact that your data may be not described with numbers at all. So not only numbers can be ordered, you can order some different things, but you should think how are you ordering them and what is the meaning of that order. Getting to numeric data, so interval data, for example, degrees of Celsius, Fahrenheit, or points of affine space. You can do everything you could with ordinal data, but here you have differences between them. They are meaningful, and you can calculate mean value. What I want you to be aware of, when I am talking about this data, you may think that interval data, it's numbers, and you can do whatever you want with that numbers. No, it's not. The problem is that when we are calculating differences with that numbers, I want you to know that you can get some new objects of some sort of different nature of what you had. For example, I have points in affine space. I can find difference between points, but I will not get a point at this difference. I will get a vector. When I am performing some different operations, I can, in the affine space, I can, for example, add a vector to a point that will move me a point along that vector, and I can find some new point. So I will get the result of that addition a new point. So that's a meaningful operation. But you cannot add 2 points. There is no meaning with adding 2 points, so you can't have that. You can add only a point to a vector. And when you are finding a difference between points, you are getting a vector. You are never getting a point. So the thing is that you have differences. They are meaningful, but that can be some sort of very different objects. In the same sense, when we are talking about temperature in Fahrenheit or Celsius, I'm always telling you that this is interval data. They don't have some sort of zero. You might be wondering why. I know that Celsius has zero. For example, water freezes at 0 degrees Celsius. But the problem is that you cannot meaningfully scale these numbers that you have. You cannot say that, for example, 20 degrees Celsius it's two times more hot than 10 degrees Celsius, or 40 degrees Celsius is 2 times more hot than 20 degrees Celsius. It doesn't work that way. And of course, you might think for some time why. But when you are calculating differences, they are meaningful. And in most formulae that you have in physics, for example, when you are calculating, I don't know, the amount of energy you need to use, for example, to, I don't know, or to unfreeze some mass of the ice, or how much energy do you get from the water when it freezes, and so on. All these formulae will have differences in temperature when they are calculated in degrees of Celsius, but they will never contain degrees of Celsius themselves. So they will always contain some sort of delta T, not T. And when we are getting to ratio data, they can do everything that interval data does, but they have true zero, and scaling of that data, it's meaningful. For example, masses. So you have a true zero, so something is massless. And yes, you can say that, I don't know, 2 kilograms, it's two times heavier than 1 kilogram. That's okay. And when you have temperature in kelvins, that's once again, that's true ratio. This scale has absolute zero, and it's meaningful to scale these data. For example, if you look at the formulae, I don't know, for entropy or for something like that, you will have temperature T there without any deltas. But these T's are measured in degrees of Kelvin. And if you are calculating, I don't know, some energy, some kinetic energy of molecules, you can once again say that if I have 10 kelvins, I have some energy. If I will have 20 kelvins, I will have 2 times more energy in that molecules. So it's really meaningful to scale this data. So that's the foremost thing I want you to pay attention to. And when you are doing all that machine learning methods, please remember that these methods are doing some math with all that features. And it's really nice to pay attention to what you can do with your features, and is it meaningful to pass them into that method, or it's not meaningful. Okay, so statistics has two main problems. So estimation of parameters and testing of hypotheses. I will not touch testing of hypothesis, but maybe you will want to know something more about that when you do some sort of A/B testing, so on and so forth. So I just wanted to know that statistics has this part, and maybe you will want to check it out. So just a few terms from there, that when we are testing something, first of all, we adopt the alternative hypothesis. So it's often called H0. So H0 is always conservative, and it assumes that nothing happens. And what you do, you are trying to perform some method. In many cases, you use so-called triple blind method. And with the information collected, you are trying to reject that H0 hypothesis. What we're more interested in is estimation of parameters. We may have some idea about, I don't know, some probability and distribution and so on and so forth. And we want to get some parameters of that distribution that will help us to describe our data. Where does everything come from? We always need probabilities because, first of all, as I told you, you can almost never get the entire population because there is too much data, and it's just impossible to get that. So you will always have some sort of sample, and sampling it's always a random process. So when you are sampling something, you will get some more or less random data, and you need statistics to analyze that data properly. Or even if you have all the population, it's often the case that it comes from some sort of law of the universe, and there is some random process in there. So once again, even in cases you have population, you may still want to employ some statistics to analyze the data you have. Okay, so to estimate something about population when sample, a few more terms. First of all, when we are saying something about available sample or population, we are trying to calculate some, well, say, fairly arbitrary function that will describe for us that sample or population. These functions are often called statistics. So statistics is not just some sort of branch of science. Statistic can be some sort of function. So don't be confused when someone uses this word in a sense of a function. Of course, a big bonus if that function is meaningful, so you can gain some insights about your data from that function. When you are trying to estimate something about population basing on the sample, and you calculate some functions on that samples, they are called they are not called statistics now, but estimators. So estimator is sort of statistics that helps you predict something about the general population. I will show you some more examples right now. And one more term that we have probably seen in the previous lecture, it's so-called IID. It's independent, identically distributed, and I want you to know this term because it's very often this property is used. And it means that something is independent and identically distributed. So you have a number of draws, you are, I don't know, collecting some sample, and you are expecting that at each draw you get some random result. This result is independent of any previous or future results that you will have, and that at each draw you have the same distribution you are drawing from. So that may be crucial when you are doing some analysis and writing some formulae, and that really helps to make them, let's say, more simple. Okay. Now, some examples of statistics. Statistics, let's say it's just some sort of function, so it does something. You may have, for example, some sample of few numbers like 263, and if you add that numbers, you already have some sort of statistics. The other question is how meaningful is that, and does it help you with some analysis? But anyway, that quantifies some property of the sample, so it may be called so. But in most cases, we are interested in special cases of statistics, so-called estimators. So when we are trying from the sample, gain some information on the population. And here are some examples of that estimators. One more thing to say to you, when we are calling that statistics, we may add the word sample. That depends on the fact whether you are applying that to the general, to the population, or you are applying that just to a sample. So, for example, when I'm saying mean, it should mean that I am calculating something on the population. So I'm taking the mean of the population. When I when I'm saying sample mean, it means mean on the sample, and this is an example of the estimator because mean on the sample should more or less reflect information on mean in the population. And the same thing goes about variance. So you have variance, just variance, it means variance of the population of you, or you have sample variance, it's variance of a sample, and you can use that as estimator for the variance of the population. Now a few more, let's say, subtle things that I want you to show. Let's start with a mean value. It may seem that mean value is very simple. So you are like having some data, you are just calculating mean, and that's all. So what can we tell more about that? But I want to say let's say, a few things that may be very counterintuitive for you. So first of all, if we are dealing with the mean of the sample, so sample mean, it's a random variable. It may seem strange for you, but calculating mean on a sample means that you have a realization of a random variable. How do you think why?
Because sample could be also like random.
Yes, because we are drawing our sample, and that some sort of introduces randomness into what we have. And that means a few interesting things. First of all, since mean is a random variable, I should tell you that mean will have its own mean. And sample mean will have its own variance. Why? Because it's a random variable. Yes?
Will those means and variances also have their means and variances? And
Interesting
so
question, because this time we are working on samples, so we did not like introduce some more randomness into them. So maybe it's not meaningful to go deeper, but at least one layer you can definitely do, because at least one time I have sampled something and I introduced randomness into there. And here is an example of how that randomness influences the result. So here I have a sort of population. So these are some numbers I have collected. And for these numbers, I can calculate mean value. That's a population, and that's just a number. Here we have it like this sort of line. So this line is population mean. That's okay. Now I'm drawing some samples. So I will draw, for example, I don't know, let me draw 8 samples and 3 samples. Whatever I draw from here are some random numbers, and moreover, we are working in the EED. So I suppose, that's my presumption, that whatever I draw from there is independent and identically distributed. So what can I have at the end of the day when I calculate mean values? I can be very unlucky, and I can draw all, for example, 3 or 9 times. I can draw just once. Or I can draw just number 10. And the mean value that I will calculate at the end of the day will be equal to 1 or to 10 in my sample. It has a low probability, let's say, let's put it that way, but it can be the case. It may happen. Of course, it's much more probable that I will get some mix of that numbers, and depending on the mix of that numbers, I will have, let's say, different results. So here is an example for sample size 3. So I'm getting 3 numbers out of here, so just randomly. There is probability of 1/10 of getting each of that numbers. And depending on what I draw, I calculate mean value of that 3 numbers, and I can get different results. These results go along the x-axis. So I can draw all 1s, I can draw all 10s, or I can draw something in between and get some value from here. And there is different probability of whatever I get from there. And you see this histogram, it shows you the probabilities of drawing, of getting different means in my sample. So now you should feel that this is really a random variable. You are getting some sort of random result, and I even have some probability mass function that describes for me that random variable. So that's good. Of course, this is a good estimator in the sense that whatever I have here, if I calculate the mean value of these mean values of these sample means, I will get the real mean. So when I'm drawing even a sample of 3, but I'm doing that many times, and once again I'm doing some mean value, I'm getting closer to this line. Of course, if I draw some sample of bigger size, for example, I get 9 elements, once again I'm getting a random variable. I still have some probability of getting all 1s or all 10s. That's okay. But it's getting, let's say, more spiky. So you have more probability of getting closer to the real mean in the population. But of course, most cases you will miss that exact mean, you will get something close to that, and so on and so forth. But this is a crucial point, like, I don't know, you should have that in your mind and understand that when you are calculating something on the sample, you get just some sort of realization of random variable, and that realization can be anywhere, and we are just, I don't know, maybe we are just lucky and we are getting close to this peak, but we may be unlucky and get somewhere far away from that. So that's the crucial point that I want to show you. Of course, all the rest estimators, they are sort of random variables as well. because we have a random sample, and that introduces randomness into all the calculations that we have. So estimators, they give us some number basing on the given sample only. And it would be very good if we can be sure that our estimators gives for, let's say, a mean sample result close to the to corresponding statistics for the population. But can we be sure of that? And the answer is that sometimes yes. For example, I showed you mean. You can do that with mode or interquartile distance and so on. So there are some estimators that you can be sure that you get more or less close to the real value in the population. Sometimes we cannot, but we can fix the situation. I will show you that with the example of variance. So when you are calculating a variance on the sample, and you want to use that as the estimator for the variance in the population, you should calculate so-called unbiased variance. So you will have two different formulae for variation, and depending on that, are you calculating it on the population or are you calculating that on the sample? I will show you that a bit later. And sometimes we cannot be sure that we get some meaningful result, and we cannot fix anything. So for example, you cannot fix standard deviation, at least if you don't know anything on the distribution in the population. So if you have some ideas what's going on there, probably you can do something. But if you don't even get the slightest idea, so there are some numbers and you're just drawing from there, you don't know what's in there, it can't be helped. Okay, so getting through estimators. So central tendency estimators. One of them I showed you, mean value. Here's the formulae. So as the function on a random variable, you can call that expected value. So there are some functions defined for random variable x that mirror central tendency estimators. These are expected value. Here is expression for continuous variable, and here is expression for discrete variable. Here you see a small picture of that. So we have some sort of distribution. We have mean value calculated for this distribution. Okay, median, once more, central tendency estimator. Depending on what you are dealing with, is that continuous distribution or discrete distribution, you will have these two expressions. Regarding median, when we are thinking about continuous distribution, you may think about like, where do I draw a vertical line that will divide my probability distribution function, my PDF, into two parts, such that I have 50% of area under the curve on the one side and 50% on the other side. So it's the question of drawing such a line. The other thing I want to show you, because you probably have seen how to calculate median in case of some discrete numbers, and we all know that when we are doing some sort of programming, we are calculating that median values by just arranging our numbers in some order. So let's say in increasing order. And then we are taking some, let's call it central number. Yeah, so we know we have 10 numbers, so we'll take the fifth number or something like that. And what does it have to do with the formula for this continuous distribution? I want to draw you this small picture. So this is a histogram. So we all know that histogram is some sort of discrete version of that continuous drawings of these PDFs. So you can think about it like PMF, so probability mass function, and it is discrete analog of probability density function. Now think about it, that we want to have 50% on one side and 50% on the other side in this histogram. So what I do, I'm treating these blocks as some sort of beads, and I'm using a thread to put all these beads on that thread. So you see how do I do that? And now I'm pulling that thread into two sides, and this arranges me the numbers in the increasing order. And taking the median from here, so like this central number. So I have these numbers, 7 numbers here, and I'm indexing them from 0. So I'm taking number indexed with 3. This is the same thing as getting 1/2 of this area on the one side and 1/2 on the other side. So these blocks are some sort representing some parts of the area, and finding that central number, it's in a sense finding where are we when we want half of these beads to be on one side and half of them to be on the other side. So hopefully this picture will give you, I don't know, some connection between discrete and continuous cases for median. Here is an example of mode. This is just some sort of value of x when we are having the maximal value for probability density function. So nothing fancy here. And here are a few more estimators. So we may have some variance estimators in, once again, discrete and continuous case. We can calculate some sort of moments, standard deviation, so on and so forth. You may have skewness. It has a complicated formula, so I'm not showing that to you right here. But I want you to have some intuitive idea what is it, what it describes. So here is an example. I have skewed left distribution. I have some normally distributed data. In this case, you see that mode, median, and mean, they coincide. Or I have skewed right. And you see that mean, median, and mode, they are arranged in a particular way, and you would see this pattern throughout different distributions that you explore. Kurtosis, once again, a complicated formula. This means the tailedness of the probability distribution. It can be short-tailed, heavy-tailed, fat-tailed, long-tailed, so on and so forth. And you can put that into numbers by calculating kurtosis. So maybe you will need that. Okay, what else? Some physical interpretations. So for example, for mean value, if you have all that probability distribution function, mean is like center of mass. So you are searching for the point that, and you use this point, I don't know, you can balance that figure on that point alone. Or when you are calculating variance, you are rotating everything around center of mass, and you have some moment of inertia, and this moment of inertia is actually equal to the variance. So some sort of reminder from physics that the same formulae are used in different branches, and in physics you call that moment of inertia, and in statistics you will have variance, and so on and so forth. Okay, so here is an example of some sort of distribution, in this case, binomial distribution. I'm just showing you that if you want to have some data on the distribution, don't hesitate to look into Wikipedia, and you will have this sort of nice table that describes your distribution. It gives you here probability mass function because it's discrete distribution. In case of continuous, you will have PDF probability density function. You have CDF here, mean value, median, mode, and so on and so forth. Even skewness, kurtosis, entropy, and many other interesting formulae. So you can check that for most of the distributions. People have done that for you, and I think it's really nice that you can have that information only in a few clicks. Okay. How much time do we have?
25 minutes.
25. Okay, I guess I can get through variability or range statistics or estimators if you use them to estimate population in that time. Okay, so it's really useful to measure how spread out are the numbers in your sample. So it may be different like cases if you are measuring something, and you may even expect that what you are measuring is some sort of constant, but you will always get different numbers due to some randomness in all that measurements and environment influence and so on and so forth. So you will always want to have some idea of how spread is your data and what you can do with that. And to measure that, here are some commonly variability measures. Of course, you can think of even your own functions, and it's not like something forbidden. Just the thing is that we already have some let's say good estimators and good statistics that we are using, and it's probably good to start with them. But of course, you may have your own that's really okay. So for example, it's range. So you are checking what is the range of numbers that you have. That may be so-called interquartile range, IQR. Do you know what that's?
It's kind of like a median, but in other
third
percentages.
quartile minus first quartile.
Yes.
Yes. So you are arranging your points. You are splitting them into 4 parts, and you are like working with 2 central parts of that points. Well, maybe I'll even draw that. I'm not sure if we will need that, but let me make at least one drawing for today. So if you are measuring some data, you can put it on the real line, and you have some numbers here, some here. Okay, how many numbers do I have here? 3, 4, 5, 6, 7, 8, 9. Let's do some more. 10, 11, 12. I guess 12 will be good enough. And I have some numbers. I have put them onto the real line, and I split that into equal chunks. Like say 3 numbers are here, and 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 I'm calling that quartiles. So interquartile region, I'll be interested in how spread are these 2 internal these 2 quartiles. So that's what I'm aiming for. And as you might guess, why am I aiming for that 2 quartiles, but not for the rest 2?
Because most of the data will be represented as quartile.
Well, you are splitting your data into, let's say, equal chunks. So each of the quartiles now has 3 points.
Oh.
The thing is so-called outliers. If we are expecting that what I'm measuring is some number, let's say near 10, I will be expecting that all my numbers are close to that number. So I'm measuring something and I'm expecting that everyone should be close to here. So I don't know, here is some number 10, for example. And if I have some outlier that is far, far away, it gets from 10, I don't know, I have, 100. So it's somewhere here, so 100. That will be an outlier. So something went wrong. I have measured something, I don't know, some external influence, my device broke, so whatever happened, I'm getting a really strange point. And when I am taking this point, it will always fall into some sort of these external, let's call them external quartiles. So when I am removing them, I am basically removing that outliers. So this is the main reasons. So I don't want some extreme values in my data set. Okay, and probably you will be you will be working with all that outliers, and you will do that many times, because when we are collecting data, we never have some ideal data, but we always have some outliers, we always have some noises, and so on and so forth. So in some cases, you may be willing to remove some data to get rid of the outliers. Okay. What else? Range. So I can estimate what I'm having there by just calculating range. It's just maximal value minus minimal value. Okay. So range belongs to L statistic, is a statistic or function on a data set that is a linear combination of order statistics. So L stays for linear. Okay, so the case order statistic of a statistical sample is equal to its case smallest value, and M is first order statistics, and max is the nth order, and so on and so forth. So interquartile range, I'm showing you how to calculate that with Python. So here is some sample, and we have a really nice function in NumPy, so-called percentile. It's when you are dividing your data set not into 4 but into 100 parts, but of course I can get quartiles from that by calculating 5th percentile or 25th percentile or 75th percentile, so that's easy. Interquartile range can be easily calculated by just taking minus of that percentiles, so that's easy as well. Here's an example of plot for you. You'll be probably using that. It's called a box plot. It's an alternative to the histogram of the sample. It shows you median, first and third quartiles, and it has some vertical lines, whiskers, that are indicating variability outside the upper and lower quartiles. In some cases, they are calculated as some sort of interquartile distance multiplied by something or something like that. So when everything that falls out, it's an outlier and it's plotted as individual points. So here an example of sample, you have an outlier 15, and all the rest data is just numbers 1 to 6. And you can plot that with function boxplot of matplotlib. And here is an example of how that looks like. So this line is median, and this box shows you interquartile distance. Here is an example for distributions with different skewness. So when you are looking at that plot, you can get some idea about how skewed is your distribution. For example, if it's skewed right, you see this picture, this green triangle, it's mean value. So you are seeing mean value, median, and so on and so forth, many outliers. If it's not skewed, you see this nice symmetric picture. If it's skewed left, you see this picture. Sometimes we want our distributions to look like normal distribution. It may be beneficial in many cases because many of our methods, they rely on the fact that you are using some normally distributed data. And when you use that data, when you use that methods on something that is not normally distributed, you may have some problems. And to make your distribution like less skewed and so on, we can use different transformations like Box-Cox transformation or Johansson transformation. I'm not getting into that right now, but you can check these things in Wikipedia. And I can tell you they really help because I even used that for analysis. So yes, in some cases, you may want to do that. They need some parameters, so you need to do some sort of minimization with respect to that parameters in some cases and so on. But yes, they help to normalize, let's say, your distribution. Okay. A variance estimator of a variance. So why do we estimate a variance? So we love variance because it has some sort of nice properties. So the main properties are written here. So I have variance of variable x multiplied by c. I can take out this c from the variance, but it picks up this square. So we can compare that to mean value. And when calculating mean value, I could do the same trick, but I just got this parameter c outside the mean value. For variance, it picks up this square. When I'm calculating variance of when I was calculating mean value of the sum of two random variables, x and y, I just got the sum of means, nothing more, nothing less. But now when I'm doing that with variance, depending on the situation, I will have a bit different formulae. For example, if x and y are uncorrelated, or often we may have even a stronger condition like independency, we can write variance of sum as sum of variances, but it's just for uncorrelated x and y. If there is some correlation, we have a bit more complicated formula right here that involves a so-called covariation of x and y. So once again, we have some sort of sum of variation x and variation y, but we pick up this term like covariation. And you can see this looks like a cosine theorem. So this covariation is some sort of cosine of something, but what exactly that is, I can tell you right now. So maybe if we have some time, we will see that in some of the future lectures. If not, just want you to see this formula and to think about how it looks similar to the cosines rule. Okay, and one more thing to mention. When we had mean value, the mean value for the population and mean value for the sample that we were calculating, they were basically the same. So we had the same mean value for one and for the other. And it may look a bit strange because in one case we are doing that just to describe the general population that we have. In the other case, we use that mean as an estimator for the general population. And it's really nice that we have the same formula, but you might guess that in different cases, it will be reasonable to have different formulae when calculating something on the population and calculating something on the sample. And here is the first case that we see, it's variance. We can, well, you have probably heard about, we have so-called biased and unbiased variance. And it's and it's really interesting why. So we have this expression for the population. You see this n in the denominator. And when we are calculating that for a sample, we have n minus 1. Many people are wondering why this is the case, and to show you that there is some sort of interest to that, here are some, at least a small part of the videos on the YouTube that promise to explain to you why this is the case. So why do you need this sort of correction? And so we have a comment in chat. Okay. Yes, fixed.
Sorry about that. I didn't.
Don't worry. Okay. So let's continue. So probably you might guess with this number of videos that it's really an interesting topic, and it's really interesting to understand why do we have this sort of difference, also called Bessel's correction. Okay, so here I show you just some sort of practical example, just to let's say, I don't know, in some sense justify or show you with the experiment that what we calculate really has some meaning. So here is a sample, just some numbers, and I can calculate with the statistics model or with NumPy, whatever I do, I can calculate either biased or unbiased variance. So, and here is from statistics model, for example, you call p-variance to get biased sample variance, and you see number 5 and 9, so something like that. Or you can use unbiased by just calling variance. So remember, these two functions are calculating some different things. And for some reason, I'm calculating standard deviation. And here is example, you do that with NumPy. You use the same function var, but you can use this parameter dd of equal to 0 or to 1, and you will say to NumPy, do you want biased or unbiased variance? And you see that numbers are different. And here is probably an example that will show to you. Here is an example that will show to you that it really has some sort of meaning, because here I have population. Here I calculated the variance of the population. It's 4.9. And you see that unbiased variance is perfectly equal to that. But the mean of biased variances is not equal. Here you see the word mean of variances, mean of variances. So we are returning few minutes ago when I was talking about the mean value, and I told you what? That mean value is some sort of realization of a random variable. Why? Because we are sampling. Sampling is a random process. When I'm calculating variance on a sample, once again, that randomness makes my variance a random variable. So when I'm doing that sampling and resampling for some number of times, so for example, I don't know, 5 times, 10 times, 100 times, whatever, I will always get some new sample and I will get some different number for variance. If I take a mean value of all that numbers that I have, I should be close to the variance in the population. Let me once again draw some small picture, because I'm feeling like this is some sort of point of confusion. So I just want you to feel that. Okay, yes, I can remove this. So here lives my population. Here it is. So I have some data in here. From this data, I can calculate some sort of statistics to get idea of what's going on with all this data. So I can get from here, I don't know, I can get some mean value from here. So I can calculate that. I can get some variance from here. So that's pretty okay. But this is population. This is all possible data in the world, well, connected to the problem I'm solving, and I have collected that in here. But in most cases, I don't have that. I have some sort of sample. What it means, I perform a sampling process, and I'm getting some sample from here. When I will do some calculations on this sample, I can once again, I can calculate some mean value. I can calculate some variance. This is sample 1, so I call it sample 1, and I endow this with index 1. But it may have happened that I have sampled some different sample. It may have its own mean value, its own variance, and so on and so forth. So what it means for the estimator to be, let's say, a good estimator. So I want with having these data, so I'm having just a sample, with having these data, I want to get some idea about this. So this is what I have. This is what I want. So when I'll be treating this as something good, it's when I have it's when I have many, for example, samples, and I will say that the mean value of all these things will give me the same result as in here. So I'm doing sampling, I'm doing many samples. So some sample N so I will say that my estimator is good when I will take the mean value of all these things together So mean of all these is, and I will get the same result as this one. So if they are equal. And probably at this point, you may really think, well, it's not obvious. Why will I use the same formula for mean here and for mean here? And you will be right. That's not obvious. You should prove that. Of course, we can prove that it just so happened, and it's really nice to have this property and don't think about, let's say, biased mean and unbiased mean. So you don't have biased and unbiased mean just because it so happened that formula here and here, they just coincide. They give you what you want for free. But it's not the case for variance. If I take mean of these things, and I will compare them to the variance of the population, once again, I want them to be equal. And once again, you are thinking, well, it's not really obvious why formulae for this and that should coincide. And they don't coincide. They don't coincide because you calculate this. I will even put a prime here with a bit of different formula than you use it in here. So when you are using variance as an estimator, you use a different formula. And the first step to understanding that is to understand the fact that you don't have any reason for that formula to coincide. I will explain you why do you get exactly that n-1 in there. But the first thing is to understand that you don't have any reasons for this formula to coincide. Here is one more nice example for you that shows you that this effect really exists. Here is some sort of population. I have drawn that with this sort of distribution. I guess it's some sort of normal distribution, if I remember correctly. It doesn't really matter, but anyway. And here with the green line, maybe you don't see that behind the blue line, so here it is. So this is the green line. That's the population variance. So I just took all data I have and I calculated variance. So that's easy, that's okay. And here are biased and unbiased variations that I calculate in here. So you remember I have that quotient, like I'm dividing by n or I'm dividing by n-1. So I get a little bit different numbers. And here are different plots that I have. And when I'm calculating mean values, because once again, these are random variables. Variance of the sample is a random variable. So this is the probability mass function of that random variable. I can get different results depending on what I have sampled from there. And I have different probability mass functions. And of course, since I have different probability mass functions, I will get different mean values for these two distributions of variances. And when I calculate them, I get this red line for mean biased variance, and I get this blue line for mean unbiased variance. And of course, you might guess, if I am making number of samples bigger and bigger and bigger, that quotient, the difference between n and n-1, it almost goes away. The bigger is n, the less it matters. Do you divide by 100 or by 99? It doesn't really matter so much. So we are getting closer and closer. So for big samples, you may use the same formulae and don't get into problems. But for big samples, of course. But you will never get that thing exactly to 0. You will just get maybe close enough. The first thing, and the second thing, well, if we have unbiased variance that gives us perfect results, why don't we use that? Okay, and now the reason behind this. The reason behind all these things, and that n and that n minus 1, so on and so forth, is mean value. It goes this way. So when you are calculating variance, so let me find some sort of, let's look at this formula. So you are subtracting from each of your data points, you are subtracting a mean value. If I am calculating that for the population, I'm using here the real mean value, the mean value for the population. But what happens if I'm calculating variance for a sample? What kind of mean value am I using there?
Sample mean, in case we don't know the actual mean, because
Yes.
sample variances can be calculated like if we know or if we don't know the actual mean. So there are two different formulas. And when we know the actual mean, the sample variance will be unbiased, as I remember. And when we don't know, when we substitute the actual mean with the sample mean, we will get the unbiased estimator that will need Bessel's correction to be unbiased. We'll get biased, and we need to be corrected to be unbiased.
Yes, absolutely correct. Yes. So if we are doing something with a sample, we will have here a sample mean. And that is the main reason behind this correction. So when you write all that formulae and do all the transformations, you will see how it comes up. If we have known the exact mean that we have in the population, I don't know, some information given from, I don't know, from somewhere, from space, someone just came and told us that in the population we have this sort of mean, we could have used that mean and there will be no reason for any correction. So we will get our variance as exact as you might guess. So no corrections, no need for that. That will be very nice and very good. So yes, the main problem is this mean, because we have sampled something and in that sample, the mean value may differ from the population mean, and that introduces all the troubles with that biasing and unbiased. Really, really good. Okay. Let me check just a moment. Let me tell just few words about the standard deviation, and we make a break. Yeah. So one more estimator is standard deviation estimator. It's more troublesome because we don't have a general correction for STD. The main problem is square root. So square root intermingles and we can't get rid of that, and that's the problem. So you can't unbias that. But in some cases, if you have some additional information on the family of underlying population distribution, that may help you. For example, I can do some correction if I know that my population has a normal distribution. So here's a formula for you. So this D, it's the correction. So some different formulas for this STD. And I will show you just an example how that looks like before we go to break. So no, so I'm not getting very deep into that. But here's an example. So I have, once again, I have a probability distribution I have drawn my sample from. this is some sort of normal distribution. I'm drawing some samples. So here is the size of sample, let's say 5 numbers. I'm calculating STD with this formula, and I'm checking for the parameter D. So here is my parameter D. I'm changing that parameter, and I'm looking what happens to all these things. And for normal distribution, it should be close to 1.5 to get more or less my STD corrected. So here I am increasing. So getting to 1.4, almost there. 1.5 looks even a little bit too much. Yeah. So when we are getting further, once again, we get some problems. So you can find some sort of constant here that will correct for you that STD, and I'm showing here different sizes of samples. Of course, with the bigger size, this correction influences less than if you have some small small sample, of course, because once again it's n minus d. So if n is big, I don't know, 1,000 points, it doesn't really matter. Do you divide by 1,000 or by 999? So you can still correct something with standard deviation estimator, but you should be really careful with that because you cannot always make that estimator work. You should know something about the underlying distribution, and you can and if you know something, for example, you know it's normal distribution, you can use this formula and get this value sigma unbiased. Okay, with that being said, I guess we can make a break, and then we will return, and I will tell you about a really nice method that we all love, and I want you to know about it, so-called maximum likelihood estimation. So, okay, a break. Maximum likelihood estimation. Let's consider the following problem. So I have some sample that is drawn from a distribution that let's say from one of the possible distribution of the family of distributions. It may you may think it's like very convoluted. So let me put it in more simple words. So for example, I have some sample that is drawn from normal distribution, but I don't know the exact parameters of that normal distribution. So in some sense, I don't have an exact distribution. I have a family of distributions. So all possible normal distributions with all that like mean and variances and so on. And the question is as follows. So for example, I know I have sample drawn from some normal distribution. Which exactly? So can I somehow guess or estimate, let's say it, parameters of the normal distribution just basing on the sample that was drawn from that distribution? And of course, it's quite reasonable to think that probably yes. Why not? If I am drawing some points from the distribution, they are carrying some information on that distribution. So if it's normal distribution, of course, it's more probable to get some points closer to the maximum of that distribution. So we might guess that there should be some method that will allow us to estimate the exact parameters of the distribution. So now we will consider this method. It's called maximum likelihood estimation. And I will show you how to use that in different cases and what can we get from it. It's very versatile method, so probably you will be able to use it at some point when you are analyzing some data. So first of all, we have a sample. How is this sample drawn? As previously, throughout all this lecture, I am supposing so-called IID, so independent, identically distributed. What it means, independent. So each of my draws is independent on the previous or the future draws or whatever. So they just happen. They don't influence each other. The second thing, I assume that they all are drawn from the same distribution. And that's pretty reasonable, because if I have data points drawn from different distributions and I don't know which one is which, well, how can I even formulate the problem in some sort of meaningful way? So when they are coming from one distribution, they are carrying some information from there. When they are coming from very different distributions and I don't know anything on them, well, it's complicated. So at the end of the day, what do I have? So for this sort of random variables, Fn, my probability to obtain the sample with some sort of given parameters will be a result of multiplication of all that probabilities of getting each sample. So I need that independence to write this multiplication. Otherwise, I cannot just multiply probabilities. And I need that identically distributed part to say that all these functions f, they are basically the same function because they all are drawn from the same distribution. And at the end of the day, what I want from that, when I'm getting this quantity, so I'm getting the overall probability of getting that sample from a distribution with given parameters theta. I want to find the maximum with respect to that parameters theta. So I'm fixing my points and I'm trying all possible theta parameters. And at some point I will get some maximum of the likelihood, and that will indicate to me that this is the best choice of the parameters. So here are a few examples how to do that analytically. So if I have a Bernoulli distribution, so once again, it's a family basically of distributions. Why? To get one exact distribution, I should fix this parameter P. So it's a Bernoulli trial. So that is the probability of getting some outcome 1, and 1 minus P will be the probability of getting outcome 0. And if I have a sample, so I have drawn n times, I have drawn something from there, so I know whether I had 0 or I had 1. I have some sort of number of successes, so on and so forth, but I can calculate that likelihood. Here is my formula. Well, this is basically a logarithm of the likelihood. You will often see this logarithm. It's not like it has very much of a meaning, but it makes your formulae simpler. You may ask me why and why do we use logarithm and so on. Here is some sort of reason for you. If I am searching for a maximum of a function, so suppose I have some function and I want to find its maximum, so some function f. If I apply to that function some different function g, so I will calculate g of f, and I know that g is monotonically increasing. What can I say about the maximum of the composite function g after f?
Probably infinite.
No. Let me draw that for you. I guess here is the. It's a nice place to think about math. Okay. Ooh. Okay. So let's consider some simple case. So I am mapping, I don't know, from R to R. And I'm doing that with the function f. And this function f looks something like this. So I have a maximum here. And I'm interested in, let's say, this x star that tells me where is the maximum of this function. Suppose I have a different function g that maps R to R. And this function is somehow monotonically increasing. So I have something like this. This is my g. And now I'm stating a question. If I have a composite function, so what that? It's g after f. So I apply f, then I apply g. What can we say about, let's say, maximum of this function? How does it even look like?
Probably in middle.
So I had
Middle
a function.
So slightly right from the middle.
Yeah, so I had a function f. It looked like this. Now I'm mapping. So I have mapped my x from somewhere here. I take some x and I map it into here. So here is some x. I'm getting some y. Now I should get this y mapped with the function g somewhere. But g is monotonically increasing. So what it means to be monotonically increasing?
For the bigger value of y, we'll get the bigger value of ji, and I guess when we apply j to the f, we'll get like similarly the same, but it will be a more like a much steeper mountain, let's say.
Yeah. So we have this function a bit distorted, but we still have the same maximum. So you're absolutely right. If I know about the function g, that whenever it takes some values, I know some y1 and y2, and I know that for y2 bigger than y1, I will always get that g of y2 will be bigger than g of y1. Then the same thing holds when I'm putting results of f into here. So if I had that f of x2 was bigger than f of x1, of course, I'll be sure that g of f of x2 will be bigger than g of f of x1. And that's why this maximum will be still kept. So when I'm calculating some sort of argument maximum of f of x with respect to x, I get some x star, I will get the same x star as I calculate arc max over x of g of f of x. It's the same x star. So they are equal. And here is, and if you think about logarithm, you get from 0 to infinity monotonically increasing function. Well, it doesn't look like this, it looks a bit different, but anyway, you have a monotonically increasing function. And of course, if you apply that to formulae like this, and you see that we have that likelihood, likelihood estimation, because we had independent growth, we have this result of a multiplication. So we have many things that are multiplied one by another. And we don't really like to work with multiplication. So we would like to take logarithm and transform this multiplication into a sum, because it's most cases it's reasonably more, let's say, simple to work with sum than with the product. So that's the reason why you will often see instead of the raw likelihood, you will see some sort of logarithm of that likelihood. And that's pretty reasonable. It makes your formulae simple because instead of a product, you get a sum. And it doesn't actually interfere with whatever you are intended to do, because your intentions are to find the maximum, and the maximum does not change because you applied a monotonically increasing function. Of course, you can apply any other monotonically increasing function and you will still be good. Okay, so with that being said, you can do that procedure, for example, for this Bernoulli distribution. So you'll see here, I'm taking all that logarithms, doing some mathematical calculations. You should all know that from calculus 1, yeah, getting all that derivatives, equating them to 0, so on and so forth. Anyway, you get the result, and that's good. The same thing for Poisson distribution. You can do all the same things, once again, getting all that logarithms, doing derivatives, so on and so forth, you get the result. What I want you to show, like, let's say, at the end, is to give you some sort of intuition why that works. So here is an example of what are we doing. And here you see the real distribution. That's some sort of normal distribution. And here we see in blue, you see the test distribution. It's like I'm taking all possible parameters of a normal distribution, and I'm trying which one is better. Here, these points, these are points drawn from the real distribution. So I'm trying to estimate parameters of real distribution without having any information on that except this small sample. What do I do now? I'm trying different test distributions, these blue curves. For each of them, I'm trying to calculate that likelihood. I'm not even taking a logarithm not to make you confused. So just likelihood as it is. And it's what? I'm taking each of these points, I'm taking them up on that curve. That determines for me the probability of that point being drawn from the blue distribution, from the test distribution I have. I do that for each point in sample. I get these numbers. I multiply them. Why? Because they are independent. And that they are identically distributed, it means that I'm working just with one blue curve. So I don't have curve for each of them. I have just one curve for all the points. And this gives me some number. The result of that multiplication, I'm drawing here on the right plot. So this yellow point, I guess it's yellow or orange, okay, orange point, shows you where we are. So what do we get when we multiply that everything that? And when I'm changing the distribution I'm working with, you see that this number goes up or goes down. So that depends on the parameters I have chosen. And at some value of that parameters, I will get maximum. And you will see that my blue test distribution is really, really close to the real distribution these points were drawn from. Of course, everything depends on the number. So the more samples you have, the better you can fit everything, so on and so forth. And to get you like some even more intuitive idea, you can think about these normal distributions, that when I'm drawing some points from that distributions, I'm getting more points near this this maximum. So when I'm trying all the test distributions, when their maximum is far from the real maximum, I will this massive number of points, this central mass of them, will tend to have some smaller probabilities than they could have when they are closer to the maximum of my test distribution. And that's why when they are close together, it's much more probable for them to get to this maximum and to get higher value in here. Of course, it's a random process, so you can be sure that you are getting some sort of perfect score or perfect estimation, so that depends. This is example just for one parameter. Of course, you can do that for two parameters. You will have that in 3D. So now I should change sigma and mu to get my distributions more closer or more further. Once again, that depends. I have somewhere this point near the peak, and I can calculate the perfect values that will estimate what is the exact normal distribution I have drawn all these data from. Okay. Okay, I'm not telling you about that, but I'm telling you this. So a few more estimators like covariance and correlation. Once again, here are just formulae. Hopefully you all know them already. Just a reminder for you, it can be biased or unbiased. This means that depending you are working with a sample or a population, you use different formulae. I will show you better some sort of pictures. For example, here is the correlation function. And how do you find that with the NumPy package? So here I have x, y, and I'm trying to find the correlation coefficient. Depending on how many that x, y's, and so on you have, you will get matrix of some size. Correlation can be calculated at least as far as I know, only pairwise. So if I will have z, I will be able to calculate xy, xz, xx, and so on, all the possible pairs. So this means that you will always get a matrix. So its rows and its columns will correspond to which variable with which one you are correlating. But you can never get a correlation of x, y, and z like simultaneously. So you're always getting a matrix of pairwise correlations. The second thing, your correlation quotient shows you in some sense how good are your points, let's say, approximated with a line. And here is the nice picture for you. So here are different point clouds and their respective correlation coefficients. So for example, if you have almost a perfect line that, let's say, grows, so it shows you some growing trend, you will have your correlation coefficient close to 1. So it's almost 1. If you are getting your point cloud, like, let's say, more and more smeared, so it's more and more close to some randomness, your correlation coefficient will go further and further down to 0. And you might guess that if we are like collecting them back into a line, but this time line goes down, you have a negative trend, you will have your correlation coefficient closer and closer to -1. Here is example that shows you that ones and -1s, so that coefficient does not depend on the angle that line has. If the line becomes horizontal, you can consider that coefficient equal to 0, then it gets instantly to -1. So it does not show you how strong is that growth or something like that. It just shows you that points are lying on one line. And what I should warn you about correlation coefficient, it's like two facts. The first one I have stated to you in the previous lectures. So if you have correlation between something, it doesn't mean anything unless you have a model why these things should be connected. So correlation does not imply causation. So if something correlates, it doesn't mean that these things are connected. It just means that they correlate. But of course, if you have a model that tells you that thing X should influence thing Y, that influences thing Z, and you are some sort of calculating correlation between X and Z to, let's say, some sort of support your point of view, that's, of course, a pretty valid approach because this time you have a model, so you have some reasonable ideas why do these things, why are these things connected to each other, and correlation is just some sort of test whether you can like support your point of view with some data. And the second thing that you see in this picture, if you don't have any correlation in your data, it doesn't necessarily mean that you don't have any pattern in that data. So here are examples of data that is very far from being random. So here our points are scattered along some, I don't know, letter W. So here they are scattered in some square or in some ring and so on and so forth. All these data sets have correlation coefficient equal to 0. But we still see some patterns in this data, and these patterns even can be used for, I don't know, for some machine learning and so on. So you can do something with them, you can get something out of it. So for example, this last one, you clearly see 4 clusters in there. So if it's a real data, that may be a reason to think, why do we have 4 clusters there? And maybe it's really reasonable to classify these points and work with each cluster separately or whatever it tells to us. Well, that depends on the nature of the data we have. So anyway, so remember, so having correlation doesn't mean too much, and having no correlation does not mean too much as well. So it's just some sort of measurements that may support some point of view, but no more. So be careful with that. Do not overestimate what it finds for you. It just calculates for you how good the points are lying on the line, so nothing more. Here is one more example to calculate that correlation coefficients. I'm just putting some sort of point in here. I'm choosing 2 sigmas. We will have a normal distribution this case. So of course you might guess that this big square is some sort of maximum of that distribution that we will have. And these 2 points, they describe for us that, let's say, sigma matrix that we have in the Gaussian distribution. And I'm drawing some points in here. So I'm getting more and more points. And as you see, my correlation is, let's say, fairly close to 0. If I will get the thing more and more narrow, what will happen to my correlation coefficient?
It will
It
be
will
better,
increase.
like increase.
It will increase, yeah, so it will get closer to 1. So right now I'm doing a click, and it's 0.9, yeah, so almost 1. What will happen if I take this point and do something like this? What correlation coefficient will I have? Approximately,
It
of
will
course.
become less.
-1.
Close to -1, yes. Click, minus 0.9. When I'm making this round, I will get closer to what number?
0.
Yes, 0.01. So you can play around with this demo and hopefully get some intuition how this correlation works. One more example for you with all that correlation thing that you may find maybe more or less nice. Here is once again an example of data points in 2D. These data points represent, of course, for me, x's and y's. So one of such points mean that I have some 1x and I have 1y, and I'm calculating correlation between that x and y. At this moment, I cannot tell anything about correlation because
We have just 1 point.
yes, and correlation shows me what?
Division by 0.
Correlation shows me how good points are lying on the line. I cannot tell how good does this point line on some line because, well, it's just 1 point. If I have 2 points, I can perfectly draw a line through them, and that means that my correlation will be
1.
or
-1.
yes. So it can be 1 or it can be -1. So that depends. Now what I want you to show, if we check, where do I have it? Any of these formulas, don't basically care. I want you to pay attention to whatever we have in these brackets. So disrespect all the rest thing, whatever we have in these brackets. So here is xi minus min x and yi minus y mean. And what I want you to think for a moment, when does this expression become positive? Maybe let me draw it on the table. It will be a little bit easier for you to think about it because I want you to see demo and formulae at once. So I have something like xi minus x mean times yi minus y mean. And I want this thing to be positive. What can I tell about these things in brackets?
They are both positive or they are both negative?
Yes, they are either both positive or they are either both negative. So that's the positive case. If I have, if I want them to be negative, I can expect that one of them is negative, one is positive. Now let's return to the demo that we have in here. So now you see in this demo only 2 points, and you may be wondering, what are these colors? So this point where all these colors intersect, it has coordinates of the mean value over x and the mean value over y. So whenever my point lies, let's say, in the red region, it means that it has values of x and y bigger than mean value of x and mean value of y. Or it has its x and y values smaller than mean value of x and mean value of y. And that corresponds to the case when we have that brackets both positive or both negative. And this means that it goes with the sign plus into that sum when we are calculating correlation. So I can get my correlation smaller, for example, putting a point somewhere in the blue region. I can get it bigger, putting a point in the red region. I can move a data point, and depending on the region it gets to, it will get as a plus or as a minus to the overall sum and to the overall correlation. So hopefully you will find this demo useful for you, and once again, you can play around with it. You can understand why points lying on the line will get to correlation almost +1 if it goes up, and almost to -1 if that line goes down. So right now I made it almost 0, but if I remove some points, you can see what happens and what we get as a result. So it's almost -1. Okay, so that's the correlation. One more warning for you that if you are describing a data set with some sort of statistical information, be careful with that because you can never get an exhaustive description of your data set. And here's an example for you called NCOMB's quartet. Here are 4 data sets. Do you see anything in common within these 4 data sets? Do they look like each other?
No.
No, they don't. But if you don't see them, if you only have some bare numbers in a table, and you calculate mean value of x, mean value of y, variance of x, variance of y, correlation between x and y, if you find regression line for these numbers, or you find coefficient of determination, all these numbers will be exactly the same for all these 4 data sets, but they look very different. So here is some sort of warning for you. If you are trying to describe a data set with some sort of statistics, you can never have an exhaustive description of that. So you should be prepared to such sort of things. And once again, be careful with all of that. So you can tell that my data sets are almost the same because I have the same mean value there, or I have the same variation there. No, it doesn't. It may happen that you have something like this, and you have lots and lots of statistical things coinciding, but you still have very, very different data sets. Okay, how much time do we have?
We actually should be
finishing. Okay, so as we should finish, just 1 or 2 words, that will be more than enough. Basically, in some sense, I am reintroducing the things I have already shown to you in the lecture number 1, so it's not like you are losing something. I just want to add a little bit more to that, some mathematical layer to that. So we talked about different models, and I told you words like high bias, high variance, or I told you that it's called like some sort of underfit, overfit, so on and so forth. So what I want you to introduce now, there is one more statistical thing to machine learning. It's called bias variance decomposition. So when we are talking about all that things in terms of mathematics, so I told you that we are basically searching for some function that should be close enough to some perfect function. Yeah, so you have a machine learning model. So it's some sort of box, you are putting some data into it, you are getting some result out of it. Of course, you can treat that as a function, so it's nothing fancy here. When we are doing learning process, that means that I have, I don't know, a number of such boxes, and I'm trying to find the best one that will suit to my needs. So that will be the closest one to that perfect function. And I'm performing some sort of training. And when I'm performing that training, depending on the data sets I have, I can get, well, say, different outcomes. And that depends on the data set I have, that depends on the family of the functions I'm searching within. So I'm defining that family with the model, with the machine learning model I'm using. So whether you use a neural network, you are creating that neural network, some architecture of that, you are basically defining some a set of the functions you will be choose from. If you are using support vector machine, you basically defined a set of functions you will be searching within. And the thing is, if you do all that things, you can show that the mean error you have over all possible inputs. So these formulae look very complicated, so I'll try to understand that in some sort of more hand-waving way. So when I'm trying to find some sort of square of error, so here is my perfect function, here is what I get from training on some data set, and I'm trying and I'm finding mean value over all possible data sets of, let's say, fixed size. And whatever I have from here, this is sort of error that still depends on the x. I'll take mean value over all possible x's. This is my total error, my total expected error that I get after, let's say, training. And it can be decomposed into these two parts. One is variance and one is bias squared. And basically, these bias squared and variance, they are responsible for the total error that you have. And depending on what you do, you can try to make your bias smaller or your variance smaller, so on and so forth. That looks very mathematically, but the truth is that for many models you can prove exactly, and for some of them you cannot prove, but we suspect in that way. So for most of the models I know, it's more or less thought to be true, that you have not only bias variance decomposition, but you have a bias variance trade-off. So whenever you are trying to make one smaller, you will get the other one bigger, and so on. And having too big variance, it almost certainly means that you have some sort of overfit. While making your model more, let's say, stiff, you can get underfit that means higher bias. So I'm not showing that in here. This basically repeats some parts of the previous lectures. So I don't want to get into that since we have no time and you all heard that. So you can just reiterate lecture number 1. Here I wanted to show you some example, but there's too much of mathematics in there. Just some sort of getting some sort of intuition. I guess I would draw that on a blackboard once more, and then so the last example I wanted to show you that it's if we have some sort of data behind the stages. It looks, for example, like this, like some sort of part of parabola. And I wanted you to show a bit of why all these variance and bias, how do they interfere with us? So for example, I'm making a data set. So here is a real data. It exists in a real world, but I don't have all the data. Whatever I have is some so small sample of that, some data set. And suppose I'm working with such an enormously large data set that contains 2 points. And point number 1 and point number 2. And I have 2 models that I am considering for this data set. I want to train these models on that data set. One model is a constant function. How it looks like is just some sort of horizontal line. The other model is just free line. So I can draw that through these points. How do you think, which model is better?
Both are pretty bad.
Yes, both are pretty bad. But if you need, I don't know, to estimate which one gives you results, will give you results further from the actual data.
Constant will give worse results.
Okay, so we are considering that constant will give us some sort of worse results because we have some big differences in here and so on. But here is the problem. Here is the problem I want you to consider. I'm getting these 2 points, my enormously large data set, at random. I can get these points this way. Okay, but what if I get this point here and this point somewhere in here? And I draw this line. Now, which one is better? I still get my constant model like getting somewhere here. Now, how do you think, which one is better?
Constant.
Yes, in this case, constant model. And you see now what is which is the problem. If you are getting a data set, you're getting your points at random. My model with the line, with the free line, it reacts to any changes in these 2 points, and you can get that line either close to this part of parabola, this blue part of parabola, or you can get very far. What does it mean? It means high variance. Your model has high variance. That's the case. So that was the thing I was telling you about in the previous lectures. So if we have too many parameters in the model, that of course that depends on the size of the data set and so on and so forth. That's why I choose such a data set of 2 points. I can't draw for you some very complicated models. I can draw for you just some sort of lines on a blackboard. But I guess you understand the concept. So for the data set of this size of 2 points, a free line, it has too much freedom. It has too much internal parameters. And that's why that introduces to you too large variance. I can get all sorts of lines that are going somewhere this way, or this way, or even this way, and so on and so forth. So my model has too many parameters. It has a large variance, and this variance contributes to the overall error. And if I do that on some randomly sampled data set, some randomly chosen points, I will get result that is basically worse than when I use a constant. Because the constant model has less parameters, it's more like stiff. And that's why when I'm drawing these points, I will get different horizontal lines. So they can be further from this part of parabola. But overall, when I calculate mean values, so on and so forth, I will get better results. I'm not showing everything that to you because it's too much of a calculations. You probably saw it in here. So how I calculated that, so on and so forth, but just skip that for now and say that, well, that's the case. And in these cases, as I told you, you can do different things. you get, if your model has too much variance, that's what? That's overfit. So that's overfit. You saw that in a picture, how it looks like. And if you have overfit, what can you do? You can take a bigger data set. You can add some restrictions to your model. I don't know, remove parameters, add some regularization, so on and so forth. So you are trying to make your model more stiff. If your variance is okay, but you may have bad bias, it may mean that you have the number of parameters in your model is too low. So probably you may want some more complicated model, and so on and so forth. Okay. And yeah, maybe I have nice video in here, so probably you may want to look that. That's a little bit about statistic, how statistic can be misleading.
Statistics are persuasive, so much so that people, organizations, and whole countries base some of their most important decisions on organized data. But there's a problem with that. Any set of statistics might have something lurking inside it, something that can turn the results completely upside down. For example, imagine you need to choose between two hospitals for an elderly relative's surgery. Out of each hospital's last 1,000 patients, 900 survived at Hospital A, while only 800 survived at Hospital B. So it looks like Hospital A is the better choice. But before you make your decision, remember that not all patients arrive at the hospital with the same level of health. And if we divide each hospital's last 1,000 patients into those who arrived in good health and those who arrived in poor health, the picture starts to look very different. Hospital A had only 100 patients who arrived in poor health, of which 30 survived. But Hospital B had 400, and they were able to save 210. So Hospital B is the better choice for patients who arrive at hospital in poor health, with a survival rate of 52.5%. And what if your relative's health is good when she arrives at the hospital? Strangely enough, Hospital B is still the better choice, with a survival rate of over 98%. So how can Hospital A have a better overall survival rate if Hospital B has better survival rates for patients in each of the two groups? What we've stumbled upon is a case of Simpson's paradox, where the same set of data can appear to show opposite trends depending on how it's grouped. This often occurs when aggregated data hides a conditional variable, sometimes known as a lurking variable, which is a hidden additional factor that significantly influences results. Here, the hidden factor is the relative proportion of patients who arrive in good or poor health. Simpson's paradox isn't just a hypothetical scenario. It pops up from time to time in the real world, sometimes in important contexts. One study in the UK appeared to show that smokers had a higher survival rate than non-smokers over a 20-year time period. That is, until dividing the participants by age group showed that the non-smokers were significantly older on average, and thus more likely to die during the trial period, precisely because they were living longer in general. Here, the age groups are the lurking variable, and are vital to correctly interpret the data. In another example, an analysis of Florida's death penalty cases seemed to reveal no racial disparity in sentencing between black and white defendants convicted of murder. But dividing the cases by the race of the victim told a different story. In either situation, black defendants were more likely to be sentenced to death. The slightly higher overall sentencing rate for white defendants was due to the fact that cases with white victims were more likely to elicit a death sentence than cases where the victim was black, and most murders occurred between people of the same race. So how do we avoid falling for the paradox? Unfortunately, there is no one-size-fits-all answer. Data can be grouped and divided in any number of ways, and overall numbers may sometimes give a more accurate picture than data divided into misleading or arbitrary categories. All we can do is carefully study the actual situations the statistics describe and consider whether lurking variables may be present. Otherwise, we leave ourselves vulnerable to those who would use data to manipulate others and promote their own agendas.
That's about splitting everything into groups. If you have some sort of data, depending on how do you split that into groups, you may get very different results. Here is an example for correlation coefficient. So I have a number of data points. If I calculate that just for them as a one sample, as one data set, I have a correlation coefficient close to -1. If I split that into groups, I have correlation coefficients close to +1. And it's not only like for complicated statistics like correlation, but in many other cases, you may have very similar results. There is an interesting case. So for example, you have two hospitals and you are trying to get which one is better. And if you just calculate some sort of survival rate in each of the hospitals, you may say, well, hospital A has a better survival rate, so it's better. But then it turns out that you might think, well, maybe it's not so easy because what if I don't know, what if there's something more to that? For example, you can divide your patients into some groups and say that one group is more ill than the other group, so it's more complicated to treat them. And what if that more complicated cases are all getting into hospital B? So you want to split your patients into groups like patients with easy cases and complicated cases and treat them separately. And it may happen that hospital B, which looked like worse for you, will get better statistics on, let's say, more complicated cases. But what you may be wondering, what may really makes you interested in this thing, that it may also happen that taking statistics over patients with easy cases, you will still get hospital B better than hospital A. That can happen. And here is a demo for you that I wanted to show you, that here are two hospitals, A and B, and here are patients that, and you are trying to get some sort of survival rate by putting different patients who was able to survive and who was not into these groups. And the idea is, if you experiment with that for long enough, you can get this sign to be turned to one side. So for example, like now, hospital B looks better than hospital A, so it has a better survival rate. But you can make at the same time the situation so that you have survival rate for group 1 in hospital A better than for group 1 in hospital B, and you can make survival rate for group 2 in hospital A better than for group 2 in hospital B. So these two signs will be showing one side, while this overall sign will show you the other side. So, and it's very interesting case. So I really advise you to try that at home, at least for a few minutes. And that will give you some idea about the caveats that statistics has and why we can never do some sort of bare statistics, but we should some sort of bring some external knowledge of what we are dealing with, what are our models, why do we suppose it's that way, not the other way around, into the subject that we are studying. So-called domain knowledge, I guess we call that way. So that's why we need domain knowledge additionally to the knowledge of statistics and machine learning that we are now learning. With that being said, I guess it's everything. So see you next Friday.